Hello everyone, my name is Charalampos Katsis, and with my colleague Ankush Singla and Dr. Elisa Bertino at Purdue University, we're going to present our work on real-time digital signatures for named data networking. An important requirement when dealing with content distribution is to ensure the content integrity and authenticity. Current designs in NDN systems have adopted the traditional PKI for content authentication. ECDSA and RSA are two signature schemes supported by several open source NDN libraries that provide both integrity and provenance protection. A drawback of the existing signature schemes is that they introduce a significant computational overhead, adding a lot of latency to the communication. In real-time applications, it is essential to keep the latency to a minimum to maintain a certain quality of service. Our goal is to provide secure and cost-effective authentication for NDN data packets. We propose the structure-free and compact real-time authentication framework, which enables real-time digital signatures for delay-aware authentication in time-critical networks. SCRA transforms any aggregated signature into signer-efficient signature. It pushes a costly generation operations to an offline phase where the producer will pre-compute all the possible chunk signatures and store them in an in-memory table called gamma. In the online phase, the pre-computed chunk signatures for the generated data packet will be fetched and the aggregated signature will be calculated. We instantiate SCRA-CRSA, condensed RSA, in the context of NDN, as it is proven to be both signer and verifier efficient. The producer first chooses two parameters L and D such that D times L equals B, where L is the number of chunks the hash is sliced into, D is the number of bits per chunk, and B is the number of bits of the SHA-256 hash output. The message hash will be divided into L equal sized chunks. Then an iterative process of concatenating the chunk index with each value in the interval of 0 to 2 to the power of d-1 takes place. Afterwards, we hash and sign each concatenated value with the producer's private key. He needs to do this for all the possible values of each of the L chunks. The producer wire encodes the packet into a buffer and then hashes the encoded message and slices it into L chunks of D bits. Now the producer simply fetches the pre-computed signature from table gamma for each chunk I of the hashed message. Subsequently, the producer computes the packet's aggregated signature S. The verification procedure follows similar steps as the signing and the offline phase. The data packet is wire encoded into a buffer and then hashed. Then, the hash is sliced into L chunks. Afterwards, the chunk index is concatenated with the chunk bits and hashed again. The consumer does this for every one of the L chunks. Then, he uses the producer's public key to verify the data packet's signature. We propose real-time application optimizations. SCRA-CRSA performs notably better as more packet signatures are aggregated together. The costly exponentiation occurring at the verification phase happens once every k received data packets. Another approach is a probabilistic signing, where a producer can randomly sign packets and save communication and computational cost. The value of L plays an important role in the performance of our scheme. The choice of L affects the size and the construction time of the gamma table, as well as the signing and the verification times. SCRA is highly parallelizable in all of its three phases. We can leverage parallel algorithms or hardware acceleration for even better performance. We carry out two performance evaluation experiments. The first one consists of 10,000 inter-data packet exchanges between consumer and producer. The algorithm aggregates the signature per 100 data packets. The NDN CXX codebase has been used for this experiment. As you can see, the results are very promising. This experiment has been conducted on the NDN RTC video conferencing tool. We had a producer application running for 100 seconds and consumer application running for 50 seconds. We assume that the consumers are not data publishers. Our scheme signs every manifest packet just as the already adopted schemes do. All in all, our scheme can provide reliable message authentication for real-time ending applications with minimal computation and communication overhead.